right? So what is um, the a data essentially it's a big vector. And if you think about it, a vector essentially is a point in the hyperspace. Like if you only have x and y, that's one point in the 2D image, 2D dimension, right? If you have like 3 dimension, then that's one point in this 3D dimension. So if you have like a huge vector, and then basically that's one point in this hyperspace. Does that make sense? So the assumption is that, well, this image essentially it's just one data point in this hyperspace. Okay. And the assumption is that for all the cats, they should be clustered in this hyperspace. Okay. And that's kind of like you can think of these points is a mountain, it's a peak from in this hyperspace. Okay. If it's easier to understand, just think of like a 3D mountain. So that the peak of it is one image, and usually you have a plateau, which has a bunch of points. That's a cluster of cats that on that plateau. Does that make sense? So when you are, walking, keep adding noises to the image, what we are doing is that essentially we are walking from the plateau all the way, well, from one point of the plateau all the way to zero, to the bottom of the mountain. Okay. And when you are trying to generate the cats, like with a prompt, what essentially you are doing is that from walking up the mountain. Okay. And basically we need a guide to say like, oh, if I walk down the mountain, like using this path, okay, each step it's a tiny step. You walk down the mountain. And then like basically when I'm climbing up, every time I just need to climb one small step. Eventually I'm going to climb to the plateau and I will find a bunch of cats. Okay, so that's kind of the intuition behind the diffusion model. Okay, but the thing is, how do I know like why like adding noise and subtracting noise will it's similar to walking up and walking down. The and how do I know that the step I'm taking when I'm walking down is going to be the same as the step? If I just reverse the step, I will be surely going back to the path. So the key idea here is that like every time if you're just adding a noise that's following the Gaussian noise, so every step I'm adding a small Gaussian noise, okay, and then like I will making sure that's if the noise is very small, I will make sure that's differentiable. That's differentiable means that the surface is smooth, right? Differential means that the surface is smooth, like there's no cliff. You suddenly jump and you can never climb out of the cliff, right? So making sure like every step it's a safe step, and then like when I'm walking up, I will make sure like it's a differentiable so I can all the way climb back to the mountain. Okay, so the key idea is to confining the noise to Gaussian noises, and mathematically that will make sure that it's differentiable. Okay, so if you understand that kind of the intuition behind diffusion model, now let's look at the detailed math. Well, this one says the basic concept. Forward, it destroys the data by gradually adding small amounts of Gaussian noise. Reverse that, creating the data by gradually denoising a noisy code from a stationary distribution. Okay. So when we are adding the Gaussian noise essentially, each step can be modeled as this. So xt, let's say like, so basically this one says, what is the data point? Again, think this image as a huge large vector. Okay, what is this vector should be given the original, the previous step vector is this. What kind of noises should I add to this? And this one basically says this is a Gaussian noise. This one beta is a hyperparameter. So square root of 1 minus t times this x t minus 1. I think it's adding something. So basically adding this Gaussian noise. This beta is kind of like determines how big the steps are. Okay. So where's my equation? So right, so this one. So basically, this equation equals to this. So adding the noise, Gaussian noise. So if you expand this equation, what we have is that xt is basically the next when I'm walking down the next step equals to square root of 1 minus beta t times xt minus 1. That's the previous image, plus the square root of beta times this noise. This is the noise. Okay, so this is how much of original image I should preserve. This is how much of the noise I'm adding to the image. Now I'm going to get a new vector, which is a new image. Does that make sense? Okay, so and this Gaussian noise I'm adding, it's combined with 0 to 1. Okay, between 0 to 1. So all the so basically each pixel of the original image is adding a noise, and the noise vector, all the noises we're adding follows this Gaussian noise, which is normal distribution. Okay, all good, all good. And if you keep expanding this, let's define alpha t equals to 1 minus beta t. So beta t, so if you look at the equation, it's easy to understand, right? So beta essentially controls how much noise I'm adding. So like how big the step I should take. Okay, so I'm just doing a little bit, defining alpha t equals to 1 minus t. So now the equation becomes this. Square root t, this plus this. And then like we know xt minus 1 can keep expanding recursively with this equation, right? So xt minus 1, if you keep expanding it, equals to square root of alpha t minus 1, x times xt minus 1 plus this. This is the second noise, right? This is the first noise this is the first noise we added. This is the second noise we added. And both noises follows the normal distribution. This is a 0 to 1 normal distribution. All good, all good. And for this Gaussian noise, you can combining these two terms based on this equation. Basically, what it says is that if you have a noise if you have a distribution like this and this, it equals to the distribution, the same data points, but the variance got the square, the square of the variance can be added together. Okay, so essentially you can combining these two terms. You can combine these two terms into this, and if you look at this, the square of this plus the square of this basically equal alpha t minus alpha t minus 1 plus 1 minus alpha t. And the alpha t is going to be canceled out. So now, basically, these two terms can be combined as this, 1 minus alpha t minus 1. And this is the new noise. Does that make sense? So this is still like the noise that's within the 0 to 1 distribution, but the basically the now the step got changed by combining these two steps. Does that make sense? So this equation is kind of important. We'll get to it. So once that you just keep expanding this, eventually you are going to get this x0, which is the original image. X0 is the original image, right? So let me go back to this original image. So you can find a relationship between the x0 and xt with respect to all these IVAs. So if you look at this, essentially what it says is that we are basically the xt equals to this times x0 plus all these different steps, these betas times, and adding a noise. Okay, so that's that. And eventually we are going to have this. If you defining this alpha t bar equals to the multiplication of all these terms, you got like alpha bar t times this plus 1 minus alpha b bar. Okay, so essentially from here we can expand. We can kind of try to find a relationship between. This is the relationship between the previous step and this step. This is the relationship between the original image and the t step. Okay, so this equation is actually quite important later. But for now, let's we just know that this is how we come to this equation. Okay, so so this is just what we came up with. Okay, so for sampling means that the reverse step, like how do we get the original. So here, like the sampling means that like we can directly calculate xt from x0, okay, and beta t is designed such that like that. So the reverse denoising process, which is the generative process. So see how the idea of diffusion is very different from autoregressive. It's very different from of generative adversarial, right? But it's just different ways of doing this, and interesting how they come up with the idea. So the denoising process essentially keep removing the noise, and you got the original data. So basically it says when beta t is small enough, the step is small enough, to get the previous step from the latest step is also a Gaussian process. So each step we just so the noises we're adding is also follows Gaussian noise. So that's the idea. So let's see how do we then but then like the question is, how do we know what are the noises to remove every step? How do we know like what the noises to add and to remove like during each step? That's the question, right? So the idea is this. The idea is the training process is like this. For the original image, okay, for the original image, based on the sampling equation here, the xt all the way here. So we already established that xt equals to this, right? So therefore, during the training process, what we can do is that for the x0, we can generate any xt. We can generate x1, 2, 3, 4, all the way to t. All these t's, right? And then, like, for example, if we are using x0 to generate x1, let's start from x1. And then, like, we know that the ground truth is this noise we just added to get to x1. Okay? And then we use a model. Usually they are using a UNet. But nowadays they also start to use transformer in this model here. So either UNet or transformer here, what we are trying to do is that based on this xt image, we are trying to predict what was just added. Okay, so and the t as the step is another parameter to the model. Basically says well, this is the image I'm seeing at xt, and this is the t number. What are the noises that just got added? Make sense? So diffusion model, essentially, it's a noise predicting process. And you're just, if you can predict all these noises, then you can step by step reverse back to this image. Okay? But how do we train the model so that it can learn? Basically, you are defining a mean square error between this predicted noise and the actual noise we just added. Okay? And this is the loss function. Okay? And let's take a look at the loss function over here, what it is. Well, this is the actual noise. Okay? This is the actual noise minus subtracting. And this is they are calculating the mean square, the L2 loss, right? Between this noise and this noise, and this noise equals to this model. Okay, this is the model. This is the either the unit or the transformer going through the original image plus this. So basically, it's this image. So you do this, plot this, you got this one. And this model predicting the noise. And you are calculating, see if this one is the same as the grounded truth. And you are making sure the L2 loss as small as possible. Make sense? Make sense? If you think about why you are using L2 loss here, essentially, if you think about it, even though it's a noise image, you can think of, again, you can think of this as the a point in hyperspace. How many ever dimensions you have, and essentially you are trying to make sure these 2 points are as close as possible. Does that make sense? Okay, so that's why it's using L2 loss. So once you are keep training the UNet or the transform over here, eventually it learns that for giving this image, giving this number t, what are the noises just got added. Okay, and so during the training process, t equals to 1, 2, 3, 4 all the way. So let's say 1,000. Let's say big T is 1,000. X0 is the original image, and this noise is a normal distribution of Gaussian noise between 0 to 1. Okay, and the xt equals to this. This is what we deduce, right? So we know that xt equals to this. And then like taking the gradient step for this model, so for this model, every time we are making sure the noise we predict is the same as this, and just using the loss function to train this model. So gradually learns to predict this noise until it converges. All good. So the training process is easy to understand. So now let's say we finish the training. Now we have a transformer or UNet or whatever model we have, or you can have just a multi-level perception. You can just have like a fully connected layers. Either way, they can all be used. The most popular are UNet and transformer. And then like once we have this model, now we know how to generate we need to go walk through the reverse process, right? So what we have is from the xt, with the last noisy image, okay? We fed into the model and give it t number t. It's predicting the noise over here, okay? And then like basically you're combining this one and this one. You are using this one to subtract this noise. You got the image from xt minus 1. Does that make sense? But here it is a little bit more. So suppose this one's supposed to be xt minus 1, right? So people find out if you are adding a little bit noise back to this supposed to be x1 to get the xt minus 1. This noise give you a little bit exploration basically, and that can actually help the model to to generate a good image. So the sampling or the generation process essentially from the noise, you first sample a random noise. Okay, you sample a random noise. The initial step, it's a pure random noise. And then like you just keep taking the steps one by one. That's predicted by the model, and you will walk up all the way to the plateau that has all the cats. Okay, so every time you do xt minus the noise, get this mu and the mu plus, adding a little bit noise for the exploration, and just loop this like let's say 1,000 times, and you are going to walk back to the plateau. So the idea is that for any random noise in this hyperspace, as long as I know how to take all those small Gaussian noise steps, I'm making sure every step is a smooth step. I will not step into a cliff. So this is the path I find, like how to navigating through the mountain or the path that's avoiding falling to the cliff and all the way climb back or to the plateau. Make sense? Okay. So denoising this DDPI, they are comparing this, compare with the GAN, both are able to generate very good images. So before diffusion, GAN is kind of the de facto, but later, like diffusion is much more, got more and more popular. But just as like we talked about conditional GAN, we don't want any random diffusion. We want conditional diffusion. We want to give something to it and knows how to do this, right? To follow my instruction, to follow my prompt to to generate the image, right? That's what I want, not any random image. So how to adding the condition to diffusion? So if you look at the process, basically for the model to generate the noise for unconditional diffusion, you just have the number step t, right? Now for the conditional condition, we added the condition into this model as a input. So the train the UNet or train the transformer kind of to learn the condition. Okay. Again, just as the conditional GAN, the conditional can be a lot of things. Can be any just a class like cat. Can be a text condition. Can be a prompt. Photo of a moon gate. Okay. Can be a pixel-wise condition. Can be a semantic map. Can be just like a bunch of edges. You can, very similar to what we did with GAN. Okay, so let's see like all these different conditions, how do we add into diffusion? So in scalar condition, let's say just class, like say class cat, and this is the feature map. This one is assuming we are using UNet. If you are familiar, like we talked about UNet, right? So it's like a shrinking and expanding network. Okay, so it's why it's called UNet. It's kind of like this shape. So like shrinking and expanding process. So this is the feature map. So the simple spatial addition. So what we did is that in this UNet, for each layer, the cat is going through this encoding and then going through a projection, multi-layer perceptron projection, and just adding that into the feature map and as a conditional feature map into the UNet. Okay, this is one way. And then like they had some, they have some optimization. What it did is that instead of the MLP, instead of just generating one embedding, you are adding a scale embedding and a bias embedding. So the projection is projecting a longer embedding, one to represent the scale, one to the bias or the shift. Okay, and then you are multiply one plus the scale times the feature map, adding the bias. So in this way to add it in this way. So the idea is that this transformation like gives you more capability of not simply, if you think about it, what this simple pixel-wise adding does is that you are adding to the intensity. You're simply adding the intensity of the pixel, right? You're just boosting the value of that pixel, right? Whereas the scale and the bias, you kind of adding, if you, for different image, you learn, by the way, this is learnable. So for a different image, you are going to have a different bias, different scale. So for different class, you learn how to better to conditioning all these feature maps to this. So adding this conditioning capability, basically. Oh, so second, what about text condition? So like I have a prompt, I want a photo of a moon gate. Okay, a photo of a moon gate as a condition. So this one is assuming transformer as the model. Okay, so we are quite familiar with transformer now. What it does is that it's using the noise, the intermediate noise image as the query, and the text as the key and the value, and they are doing a cross contention between the Q and K, okay, and to output the feature map for the next one. There's another way of doing this. This is so-called like this joint attention. So instead of just using the Q as one modality, has the Q value, text has the key value and the V value. We are having QKV for both modality and doing cross attention between these different Qs and the Vs. Okay, so this is another way of doing the attention, trying to learn how to generate a better feature. So another way of doing this is doing the single self-attention. You are simply concatenating this text token with this image token, and then doing KQ-view, doing self-attention to generate the feature. Okay, so this is just different ways of how do you fuse the information from the text token to the image token. This is very similar to what we learned before for all those transformers. Pixel-wise condition. So this is a so-called control net. For example, like if I have a canny edge, then like I can have, based on this edge, I can generate all these different kinds of moves. And for this, if I just have the skeleton, now I can have like different people follow the same posture, right? So this is another way of condition. This is pixel-wise condition. So control net is proposed to achieve this. So what the control net does is that, let's assume this is the network that's already being trained. Let's say this is the UNet, or this is the transformer that's already being trained to predicting the noise. Okay. So what do? Is that first we make a copy, make a clone of this network. So this network is locked, is frozen. And then we got a trainable copy. So now we have two copies. When for the condition, which is the skeleton, let's say the skeleton over here, as a image, okay, going through the trainable copy, and the noise is going through the diffusion process. Okay, okay. So X is noise, and we keep generating the next noise. And what we do is that for the condition, going through this zero convolution and then like adding with the noise, trainable copy, and then like adding back to the noise. So what we are doing here essentially we are trying to using this trainable copy to kind of learn from the skeleton. So like roughly you should follow that skeleton. And then like, because this is a noise generation process, right? So basically it says, well, based on this skeleton and based on this is the noise I have so far, okay, what kind of a noise I should generate? Okay, and then using that combining with the original noise generation to get that information. Okay, and using 2-0 initialize the convolution, 1-by-1 convolution, kind of as the it's 0 initialized, but it's going through the training process. Eventually, it will learn, while giving this condition, how should I generate the noise?
We are generating the noise separately for the control, or like for the condition.
Right. So you are generating a copy of noise for this control. You are generating a copy of I'm sorry. This is not the I'm sorry. Yes. So we are generating the noise for the control and all the image and combining them. Okay. So you add them and do that like kind of so that it can follow the condition and generating the image. Okay. So later we are also going to learn another way of controlling, but this is just different ideas. Then like latent diffusion model. So what latent diffusion model essentially says, oh, wow, if I can do diffusion from image to noise, can I simply do the diffusion process on the latent space? Because usually when we are going to encode and decode the process, latent space is usually it's not much smaller, but it's smaller than the image, right? So I can just do that. If I can, from the latent space to the noise and noise back to the latent space, then I'm just going through the decoder I got of the image, and it's much faster, right? So that's the basic idea. So nothing really new. So you're extracting the feature, the embedding, and adding the noise and learn this. And then like when doing the sample generation, you're from the noise generating the latent space embedding, and then going through the decoder back to this. Okay, so this is a way of more efficient. So diffusion XL, so it works quite well. So image editing. So the basically says, well, I give you just very, all these blocks. Can you, generating the image? So I'm trying to, give me one second. So basically doing the image editing, what we are doing is that if I give you this image and I'm going to, let's say like I want to give you a couple of strokes. It says, oh, I want like adding a cloud to this. Okay. So the image and the stroke, they are two different things. Okay. So let's say like the cloud and the image, they are two different things. When we say like there are two different things, the cloud and the kind of the shape, there are two, when we are thinking two different things, it means that in the hyperspace, the image is on this plateau, and this like strokes, they are on this plateau. Like in this hyperspace, like there are two plateaus of a mountain. Okay, does that make sense? And then what this paper is doing is quite interesting. It's the first step is perturbate, adding noise to this input to make this. You can still kind of see the outline of this, but with a bunch of noises. Does that make sense? Okay. What it does is that if you think about it, the intuition behind this is that when I'm adding a bunch of noises to when I'm adding a bunch of noises to this image now basically is pushed off the plateau. It's now no longer on the plateau with the strokes. The blue dot is kind of where the image stands. Okay, so when I'm adding a bunch of noises, it's a bunch of noises not on any plateau. It's kind of stuck in the middle. Does that make sense? Okay, but it still have some outer lines here. So it's kind of like the illustration here means that now it's kind of in the intersection of these two mountains. It's like these two mountains are like middle of these two mountains, like a valley between these two mountains. Does that make sense? So this image is kind of in the valley of these two mountains. Okay. Now, if you are going through this, this diffusion process, now it kind of gradually learning that, oh, now I'm kind of coming from the strokes. Okay. I'm coming from the strokes. I'm coming from here, but it's not a real image, right? When I'm pushing off the cliff in the middle, like I'm coming from the strokes, but also it's very close to the real image mountain. So from here, if I'm keep doing the denoising process, I will gradually climbing up to the green mountain, which is the real image. So therefore, by doing this, the image will follow my strokes, but also becomes a real image. So basically, I'm kind of finding the main idea is that I'm trying to finding a way to migrate from the plateau of this kind of stroke to a real image. Okay. In order to find the path, I'm first adding a bunch of noises to push this image to the middle of the valley. And then I'm going through the diffusion process, kind of climbing the green mountain all the way so that it's a real image. But I know because it's coming from that plateau, it still keep the idea of the strokes. See how it's the algorithm always have this intuition, the logic behind this. Does that make sense? And you can see that how it works. This is a stroke. This is the prompt. So fantasy landscape trending on ArtStation C. Okay. So that's quite amazing, right?
Yeah. How are we how do we ensure that across the steps we keep the structure intact? Like the model may begin to forget, right?
So you can see that. So basically, you have the stroke adding the noise. The stroke still kind of have some of the information here. So that's kind of like you are pushing into a starting point of the image. So if you think about the green, image as the image plateau, you basically all the noises around this image can all climb to here, right? You can climb from here to the mountain, from here, all the way from here. So the stroke kind of give you a starting point. And then like the adding noise process is pushing this image to this image. And this image is sitting in between the valley of these two images. So you're setting in a good starting point. That's similar to the stroke, but then like you're climbing all the way to the mountain and give you this. And from here to here, it's a pure denoising process. So this basically it's where do I start? I'm no longer starting from a random noise. I'm starting from a noise that's pushed from this stroke. Make sense? That's really interesting, right? So that gives you very, you can see how realistic this and how sketchy this one is. So process is you're adding a bunch of noise to this and then going through the denoising, come up all the way to this. And of course, like you have also have this text prompt that means that the transformer also knows how to went through the attention process with the text prompt. All good. All good. Then like model personalization. This is also really interesting. This is called Dream Booth. Basically, it's a kind of like the photo booth. What do we want is that we're not just wanting a sketchy and generate this image. Like I have a pet dog. I want you to generate image for my pet, right? That's be more specific. Like I want you to generate image with this pet, my own dog. Okay, not like any dog. Okay, so that's the requirement over here. So with the same dog, like you can generate like all these different backgrounds, different postures. Okay, so that's the requirement for this work. So you know, if you're just using this image guided, if you using this DALL-E, then like you can see that it's not specifically this watch, this clock. This clock has a 3 on the surface, which is yellow, and on the side, but this one will actually generate an image a different 3, right? It's not the clock you want. It's not your clock. Okay, if you're just using this. If you're just using a text, again, it's not your clock. Okay, so the Dream Booth paper, what it does basically says, oh, I'm going to generate specifically this clock with the 3. Okay, and how do we do this? The idea is this. The idea is this. I'm going to give like the model a couple of my own dog image. Okay, is that like a dog or a not like a dog? It is a dog. Okay, and I'm going to have a text to image a model. It could be diffusion. It could be so here it's not most likely it's a transformer diffusion model. Okay, so text to image diffusion model. Okay, what the Dream Booth the algorithm does is that it's trying to fine tune this model to strongly associate this unique identifier like V, like square V. We know that this bracket V usually it doesn't have any meaning, right? So what this model essentially does is that I'm specifically enforcing the attention model to attend this special token to my dog. Okay, so making the model memorize this token is this one. Okay, and then like you have a updated model. Okay, and then like when doing the inference, you can say a V dog in the beach. Okay, or a V dog walking on a rainbow colorful carpet. Okay, but if you think about what is the drawback, the drawback is that for any dog you want, you need a specific model. The model can only handle, well, of course it can handle other things, but it can only, you have to have a specific model for your particular cat or particular dog. If you have another cat, you need to train another model that associates V to another one. But you can easily extend this. So you can like upload your image, your family image, your dog image, and each of the image can associate to a specialized token, right? So that you end up have a model that knows basically some secret word and use that secret word to make sure that the model kind of recall the image you just teaches it. Okay. So usually you need to associate this image with specialized token because you don't want this token to have any meaning. Because essentially you're assigning a meaning to that token right now. You don't want this token to have any meaning by itself. Make sense? Okay. Because otherwise you are going to be confusing the model, right? What this token really is.
We are adding a new token or Yeah, using some like not used token.
You can use, so this token is you are defining the token that's associated with this. So you are essentially, you have a bunch of images, you have a, you can pick one token that doesn't have a meaning. You can pick like square V, square A, square B, as long as it doesn't have any meaning. So to forcing the model remember that that is that. And you can associate multiple tokens with multiple different images so that when for that model, like whenever you input this token, it remembers what. A V dog is going to be this dog. A dog is going to be a random dog. Okay. But when, let me see if they mention this. Okay. But here, like during the training, it doesn't have this. But if you look at the paper, so when you are training this model, you need to be really careful because you want the model to know that a V dog is this dog and a dog is any other dog. Okay, so in the loss function, the author did is they are making sure they are making sure like when it sees a dog, making sure it knows that a V dog is this one and a dog, any other things is a dog. Okay, so those are basically the process that when the author did this, then they realized that well, if I am forcing the V associated with this dog, then whenever you say a dog, the model will always use this image to kiss the nose, right? But you don't want that. You want a dog to be any dog, a V dog to be this dog. Then they change the loss function to ensure like all the dogs are dog and this V dog is this dog. Okay, so that's kind of like usually the way that we do research. Okay, so next, so now like that kind of explained the all the process of basics of diffusion. Okay, so next I'm going to talk about some optimization technique. One is the sampling technique. So remember, sampling means that we are getting the image right from the noise. Training means that we are from the image to the noise. Sampling means that from the noise to the image. So sampling is the inference process. We're generating the image. Okay. So this one basically says, how do we, so remember when we are doing the sampling, we always do step by step. When we are climbing the mountain, each step we are climbing a small Gaussian noise step. So basically each number got adding a small Gaussian noise. And because why? Because we are making sure like every step is a smooth step. We are not falling off the cliff. Okay. And that's just the math property, making sure that adding a small Gaussian noise you won't fall. Okay. And you can safely climb back all the way to the plateau. But the fast sampling technique basically says, oh, I don't want to climb 1,000 small steps anymore because that's slow, right? How about, I want to just, I want to climb 10 steps and to the mountain. So you need to make sure like all these 10 steps, you are not just falling off the cliff. So that's what this is about. So people are trying to reduce the number of steps you are climbing. You are eventually people want to know how to just jump all the way, just one step. That's the ultimate goal. You want to jump out one step to the image from the noise, right? So that's the goal. So let's see like how people are pushing this step by step. So first, this is denoising diffusion implicit models. So you can see that wow, now the goal is that like I don't want to outstep, I want to jump, right? I want to jump like instead of 100,000 steps, I just want to like a couple of steps. That's the goal. So how do I know that how do I replacing? So here all the noises are generated by the UNet or the transformer, the noises, right? So each step I'm using the transformer to predicting the noise, right, and adding the back. So here basically says how can I have a model that's predicting the noise from multiple steps and making sure also like not falling off the cliff. So that's the idea. So the idea is that like this step by step is the Markovian step. Is it possible this is what we talked about earlier. Is it possible to define a non-Markovian forward process and corresponding reverse process that shares the same diffusion kernel and the loss? So essentially, we want this defining a new function that's going to generate this image and this image to be as close as possible. Okay, so that's the main idea. So the forward. Okay. Anyway, so the idea is this. So what they find out is that this. When we are adding the noise, okay, if we train the model, not just guess the noise from x1 to x2. Instead, we are guessing the noise from x0 to x2. Right? We have the jump from x0 to x2. And they find that, well, if I'm looking at when I'm guessing the noise, so remember over here, when I'm guessing the noise, I'm only looking at x1 to guess the noise that's added to x2, right? I'm just looking at the previous image and guess the noise. That's the transformer. So what they found out, well, if not just looking at the x1, but also looking at the original image, then I can have a very good guess of the noise of how to jumping from x0 to x2 by looking at both x0 and x1 to this. And for x3, by looking at both x2 and x0, and I can guess the noise that's added to here. Okay, so that's kind of the forward adding noise process. Okay, then the reverse process essentially it's a reversing, right? So basically it says, well, what is the noise coming to x2 if I know x3 and x0? Make sense? What's the noise added to x1 if I know the image from x2 to x0? That's the denoising process. But this idea has a bug. In the reverse process, you are trying to get x0, which is the real image. Right? But in order to generating the noise, I need to look at my previous step as well as the original image. How does that make sense? How does that even make sense? Right? So it doesn't make sense. So the trick is that, well, of course, I don't know what's the real x0. Of course, I don't know the real x0, but if we go back all the way to the equation we talked about earlier, of course, I don't know, what's the real x0. But based on the equation, the xt and this, I can try my best to predicting a x0. So remember why we are taking all these little steps, because we are afraid we are going to fall off the cliff, right? But I'm going to just being bold. I'm going to just from xt, I can predict a x0. Try my best. Okay, I'm just going to try my best from xt. I'm going to predict the x0, and then basically says if I'm looking at my best guess of x0 and the previous step, what it was the noise added to me. So that solves the problem of this. Of here. So see, the forward process is this. Well, by looking at the original image, by looking at x1, I'm guessing what's the noise adding to x2, right? By looking at x3 and x0, I'm guessing what's noise added to the x3. Okay. Now, when going reverse, I don't know x0, but I'm just going to try my best to predicting x0. And then basically says, if I'm looking at my best prediction of x0 and x3, what should be the noises added to to go back to x2, right? So that's kind of the reverse process. Okay. So therefore, this is the original sampling process, remember? So basically, every time we are adding a small noise and go back to the one step, right? But in this DDIM optimization, you are first predicting a small noise, and this is not the. So here is the final DDIM algorithm. So what it does is this. Instead of defining like 1,000 steps, I'm defining a step array. This is a sequence as 0, 10, 20, 30 to 1,000. And we only have all these steps. And because of these steps, now essentially we need to jump divided by 10, right? Only jump 100 times, trying to climb 100 times to the top of the mountain. Okay. And let's see what, like during each jump, what do we do? During each jump, so we define of course we have, sample a noise first. And then like for all the S from S to 1, so we do this TS, let's starting from 1,000, and T prime, let's say 900. So from 1,000 to, no, I'm sorry, from 1,000 to 990, right? Because it's decreasing by 10. Okay, so from 1,000 to 990. First, I'm sampling a noise. Okay. I'm sampling a so I'm sampling a noise, yes. And then I'm assigning the x0 bar to be the right. So the x0 bar is what we deduced from the previous equation. So this is the x0 at my current best guess. My current best guess of x0 is this. Okay? That's my current best guess. And then therefore, the xt prime, basically it's the x 990, okay? 990 equals to my best guess plus this noise. So in this way, I can guess the xt prime. So basically, the algorithm is that from this step, from the image in step 1,000, I can guess the image that's from the step 990. And you're repeating this process. So now you're hopping by 10 steps at a time. Okay. Right. So they basically shows that this is the DDIM, this is the DDPM, this is the FID. So you can see that if you are only hopping 10 times, you are hopping 10 steps one time. Every time you hop 10 steps, I'm sorry, this is actually says if I only hop 10 steps. So instead of 1,000, I'm hopping 10 steps. So each step basically it's original. You're combining 100 steps into one step. Okay. So you can see that the FID for this is 30. And for DDPM, because originally you need 1,000. Now if you only hop 10 steps, you still just climb a little bit of the mountain, right? So the FID is still very big. Okay. So but for DDIM, if you climb all the way like 1,000 steps, the FID is very, very small. 3 and the DDIM, if you hop this, you have a little bit increasing of the FID. Okay, similar performance for another data set. So that's this. Basically, you are trying to do the multiple steps at a time. Okay, that's the diffusion process. So now next, let's talk about like distillation. It's another way of trying to. The ultimate goal is I just want to jump immediately to the top. So that's kind of the goal. So what it does is that the idea is that, well, if the original you need to get multiple noises, right? So now I'm going to using this to teach a student. So the teacher, every time you are guessing one step noise. Now I have a student that learns from two teachers. Now the student basically learn how to generate the noises for 2 steps. And that's using 2 teachers to teach 1 student. Okay, and same here, using 2 teachers to teach 1 student, and then 2 students teach another student. Eventually, the student is going to learn the noises for multiple steps. So that's the distillation idea. And they see, what is this? This is the FID. This is the sampling steps. So basically, this one shows that for this one, the distillation one, this teal color, you have fewer steps to achieve a smaller FID. Okay. So this consistency model is another idea. So the consistency model basically says, well, when you are adding the noise, it's this. But when you are coming back, no matter, because I know that, like, if I'm adding more Gaussian noises to this, I know like the path is smooth, means that there is a path. Okay, there's no trap, there is a path. Okay, then what that means is that along this whole path, if I just jump from any point of this path, they should all landing to the original point. Okay, so basically the idea is that I'm going to train a model. That trying to, from in this path, any data point of this model, any data point on this path, if you feed those images to my model, they all should landing to the initial image. Okay, but how do I train the model? How do I train this model? So making sure everyone is landing to the original image. Okay, so the idea is this. Well, I'm going to make sure the model, the f theta, x00 goes to x0. So basically, is that like, if I'm the original image, I'm going to jump to the original image. So for this model, if I give you the original image, you should generate the original image. That's fine. Okay. But then basically says, well, for all these data points, when I'm trying to jump, actually I do not know where to jump because I don't know the original image, right? If you are falling off basically you're jumping from the whole climbing path, you don't know where is the ending point because that's what we want to generate. That's the image we want to find. But when you are just suddenly jump, you don't know where it is. You don't know where's the starting point. You don't know where is the oh, I'm sorry. You're actually jumping from the the bottom of the mountain all the way to the top, right? So the adding noise process, yes, I have a mark. So let's say this is the cat, okay? This is the mountain plateau, okay? When we are adding the noise, basically we are taking one step at a time, okay? But we know that there is a path. There's a path coming to the bottom, okay? So basically this one says, well, if I don't know, like, I do not know what the original image, I don't know where that is. If you simply just keep from any data point in this path, if you just jump hard enough, you are going to land somewhere on this plateau. Okay? If you jump enough, it's going to be somewhere. But I don't know where that is. I definitely don't know where the original image is, right? For sure. But the one thing I can do is that I'm going to train a model saying that, well, for all these data points, they are going to landing to the same place. So that I can control. I don't know where, but I can control like they are jumping to the same place. I just need to control the image. I just want to like the image they generated to be enforcing by using the distance enforcing they are all on the same place, right? So if I have a model, this is f theta, so I can ensure the image, the generated image, this is like the unsupervised learning, what's the name of it? The positive pair, the negative pair, the contrastive learning. So in contrastive learning, we are pushing the positive pairs together and push the negative pairs away, right? We don't know what they are, but we know that they belong to the same place. Does that make sense? Similarly, you can define a loss function for the f theta such that the loss function of the theta is that like all the generated image, they are landing to the same place. You are pushing all these to be as close as possible. Make sense? So that we don't know, and we don't need any grounded truth. We just need to push all these landing places to be at the same place. Does that make sense? And the trick is that, well, if you train a model, f theta, for any place on this path, you're always landing to this same place, then eventually I just need to make sure the f theta, this x0 equals to x0. Right? Means that while they are all landing into the same place, which is the same as the original image. So in this way, I can enforcing eventually everyone landing to the image. Does that make sense? So by doing this, now like basically I learned a model says from anywhere on this path, they're always landing to this image. Does that make sense? Okay. All right. So that's the boundary condition basically says I want to make sure the f0 equals x0 equals 0. So like making sure if I jump from here, I'm landing here. Okay. And then like the other condition says, well, everyone else has to be landing to the same place, which is the same as the fx0. Okay. So by doing these two condition, you can enforcing this you're jumping to a image. Okay. What is this? Oh yeah. So this is the training. This is the training process. So the training process basically says so the training process goes like this. In order to train this f theta network, basically I'm going to from this is xt, right? This is x0, right? So I'm going to use a normal diffusion model to from xt to predict xt minus 1. Okay? So this is I'm using diffusion model, like let's say like stable diffusion, to from xt predicting the small step. That's fine. And then like now I have two data points and also have x0. Then basically I'm saying I'm going to train another f theta model saying that, well, if you I'm entering this nt minus 1 and this xt to my f theta model, they are going to landing to the same place basically. And then I'm using the diffusion model to generate xt minus 2 and says, well, these two has to landing to the same place. So this f theta is this elevator. So basically, I'm still using diffusion to generate all those steps, small steps, but using those small steps to train my elevator. Does that make sense? Okay, and this one basically, this one basically says, well, I'm going to this f theta xt n plus 1 t n plus 1. Basically, it's the original point, and this is f theta xtn tn. Basically, it's the tn is predicted from this tn minus plus 1 with the diffusion model. Okay, so basically says, well, if I have an elevator function, and from here to here, and from the next step from here to here, my elevator should take them to the same place. And you are subtracting this two image, right? You are trying to minimize this loss, and so they are landing to the same place. Okay. So this consistency, so in this way, they can have a few step generation with consistency distillation. Okay. All right. So finally, let me talk about the acceleration viscosity. So so this is like the editing part. So basically, it says the idea is kind of simple. So if you look at the image, this is sketch, and this is like I'm adding a sun, right? So the idea is that, well, if I'm doing this, like I don't want to do the diffusion all from scratch because I already have this. And then basically I'm caching some of the image. So first I'm only going to only generate the edited part. Okay, so I only need to regenerate this. I only need to regenerate this edited part. Okay, and then like the extract the feature map only for that small part, and going to the diffusion only for that small part, and add back to the older cache. Does that make sense? So basically, I'm just chop out this part and doing the diffusion only for this part, and adding back to the image already generated before. So that because this is editing, right? So you always edit from a base adding stuff. So we make sure the background they all not changed. Okay, so that's that. So this is the algorithm process. Here we are assuming using UNet. So sometimes it's confusing because sometimes because they are from different papers. Sometimes they are using UNet. Sometimes they are using transformer. So here, like, see, the idea is basically, well, if I'm only editing, here, this is original image, and if only editing, I'm adding two clouds to the top, okay? So I'm only need to, for each step, I have active indices. So basically, I'm saying only these two parts, only those three blocks need to be generated, okay? So, and then I'm using this as a mask to extract those three parts. And only those three parts are going through the diffusion process. I'm then adding back, and then like you are going through this diffusion multiple times, eventually get this. Okay, so that's nothing fancy. Masked. Okay, so there's nothing. This is original. This is this. If you're adding a palm tree, okay. So basically, compare with node, you're improving the latency and the memory. Okay. So quantization. It's a bit messy, but well, the idea here is that if you look at the transformation, we have y equals to weight times the activation, right? So let's say this is a convolution or like a fully connected layer. We have y equals w times x. We know that when we talk about large language model, the difficulty of quantization is because of all these outliers. Okay. So we know that we also learned that the smooth quant, right? So what we did is we are trying to do some math transformation to make the outlier transfer the outlier from x to the w. Okay. So now the x becomes much smoother, but now the weight becomes harder to quantize because all these outlier got transferred to this. Right? Right. And what do we do about this? So they do this singular value decomposition. So basically, this weight matrix can be decomposed into a normal, easy to quantize matrix plus two low rank. This is like a low rank. So plus this low rank matrix. That's and then by doing this decomposition, these two matrices are very easy to quantize to 4-bit. And these two, because of all the outlier, it's very hard to quantize. We just keep them 16-bit. But because they are very small compared to the majority of the matrix, we are fine. Now, instead of the y equals wx, now y equals to w 4-bit times x 4-bit. So this is the two green part. Okay, plus this L1, L2, both of them are 16 bits times the x. Make sense? Okay, so these are the actual data. This is the illustration data. But that's the idea. So smooth quant to transfer the outlier and using the value decomposition to decompose into one big matrix that's easy to quantize and two hard to quantize matrix and leave them as it is and just quantize these two parts. Okay. And then during the computation, this is the computation process. The input got going through the unquantized part, going through the quantized part, and add them together. Okay, so basically just this, right? So just this equation, right? So go through unquantized and going through the unquantized, going through the quantized, and add them back. Okay, so that's that. Finally, parallelization. Just give me 2 more minutes. So the diffusion process is very hard to parallelize. Why? If you think about it, first of all, diffusion is a step-by-step process. It's a sequential process. Two, the diffusion, like it's a whole image. If the image is big, there are 2 ways of do the parallelization, right? One is you chop sequentially. There's no way we can chop that way. The other way is you chop like the image into multiple parts assigned to different servers, right? But in that way, because during each step, it's the whole image, right? So the communication overhead is very big. Does that make sense? So basically, if you look at this, you patch 1, patch 2, you can see every time you need to synchronize and you move. You synchronize and you move. It's nightmare for parallelization, right? So the optimization, the observation they made is that, well, because every time you are generating the input, because like when we are adding the noise, the image doesn't change a lot when every time you're adding some noise, right? So they find out the input to each layer, they are very similar between these adjacent layers. Okay, therefore they are proposing this architecture. So what it does is that for this patch 1, I'm going to feed it to instead of feeding to my corresponding layer, I'm going to feed into the next layer. Why this is the speed up? Because now when my UNet has the image to the next layer, and this UNet can process the input from this layer while I'm waiting the data from this earlier layer. So if you look at this, for this UNet, it has two data, one from my own computer, one from the other computer, right? So my own computer, of course, in my own memory, so I can have it and start to process it right away, while I'm waiting for my neighbor to send me the data. Once I finish the processing of my own data, now I can start to process the data, the image from my neighbor's data. And what is the drawback? Apparently, UNet was expecting, I was expecting the data from this stage, but now you are giving the data from the previous stage, right? Right? But because the observations that like adjacent stages, the images doesn't, because we are only adding a small beta noise. So the image doesn't change a lot. And they find out this can speed up and the image quality is still good. Make sense? And that's all for today's class. Thank you.